Good morning, everybody. Today we're going to cover Chapter 15, Section 2. I'm going to try to get the last section also of Chapter 15 taped sometime later today so that we could start Chapter 16 tomorrow. And then however far I get with the recordings on Saturday by, let's say, 6 o'clock p.m. in Chapter 16, that's as far as we'll get in the course. Because yeah, I don't want to overload you all because you still have to assimilate the stuff and then do the homework assignments and then take tests. So however far I get with the videos and I send to you by Saturday at 6 p.m., that'll be the end of the course. Anything after that will just be general knowledge for you, but it will not be included on the tests and the homework. So I'll take those off. So I want to make sure everybody has enough time to do everything. All right. So let's look at this. Up until now, whenever we took integrals, whether it's single integrals, we went from, let's say, 0 to 5. And even when we did double integrals, it was always from some number to some number. Now we're going to go to general shapes and general regions where we'll have one set bound, and then the other one will be an equation. So that going from these general rectangles to any object shape in space, it's where it starts getting more difficult. So this reorder the points or the bounds of integration. That's what we're going to do today. But we're going to look at double integrals. All right. So the first section we're talking about is double integrals over bounded non-rectangular regions. Now, why is that important? Because up until now, if we had rectangular regions, and we say when we find the area or the volume of this object, well, we can make perfect boxes, little rectangles inside there, and then number those 1 to n, and then we take the integral of that and then find the volume of the area under that curve. But what about if we had not a circle? Let's look at an oval. Well, ovals are easy also. But when we have one of these objects, whenever we try to do the perfect rectangles, we cannot use the pieces if we had a magnified. Here's the curve. We cannot use this rectangle because it's missing some of the region. Even if we increase or decrease the size of these boxes, our delta x and our delta y's, let's say those become infinitely close to 0, we're still going to have some part that's not going to be in the curve, and we can't use that part. So because of that, we can't get an accurate calculation for the area of that object. And then if we can't get the area, then we can't get the volume. Because remember, our formula for the volume was this. So we have to first, if we can't get the right area, then we can't get the right volume. That is the big problem of this. So as the cell sizes and our norm all go to 0, we still have an incomplete partition of this object. All right, so that is what we're going to try to look at today. A double integral of some function over some region is actually defined as this. It's the limit as the norm. Remember, the norm is the largest of the delta x and delta y's. And it sets all of them to that, so it has a more uniform distribution. The limit of the summation of I from 1 to n of, let's make it k, x sub k, y sub k times the delta A, the area. Remember, this is called the Riemann sum. As we take the limit, as our delta x and delta y become very small, our areas become more accurate. And then as we add them all up, we in essence get the double integral with respect of over the domain of our function f of x, y, because remember the area is the delta x times delta y. That's what delta area equals. So our whole objective here is we have to look at the function itself. This is a point in the function, and this is the area of the projection of it, which we'll call a shadow. And now, again, the hardest part of this section is going to be how we define the bounds of integration. The issues with the boundaries of R are these. When R is a curved or has a curved boundary, the n, out of focus, the n rectangles that we have of the partition lie inside R, but do not cover all of R. Because if we had our object here and we do our small rectangles, some parts of it are not in the R range. This is R. That is a problem that we're going to be faced with. So the one way we can fix that we try to fix that with delta x getting infinitely small and delta y getting infinitely small. But even at that, the partitions are the norms as they go close to zero will never accurately capture the entire region R. So this issue occurs. It's okay with circles. It's okay with ellipses and any polygons. What it's not okay with is with our non-continuous graphs or polygons of inconsistent bounds. So there we can, inside here we have our boxes. As we make those boxes smaller, it's not going to help. So for our course so far in this level, we'll stick with circles, ellipses, paraboloids, and rectangles. Let's define volumes. If we have a function f of x, y, and it's positive and continuous, which means it's differentiable, over some whatever region R, the volume of the solid between R and the surface of the solid z equals f of xy is defined as the double integral f of xy dA, where that's over the region R. Okay, now why is this the volume? Because remember, area is made up of x, change of x, and change of y. This is the square. This is the height of it. So now what this gives us is a three-dimensional object, which gives us a volume. Okay. So far, that's pretty straightforward. But here's where the issue comes in, the difficulty, not the issue. If the region R in the xy plane is bounded above and below by curves. In other words, we have y is defined as some function of g that could be above, and y could be defined as some other function of g. So this is the reason now this is difficult, because these are non-rectangular, non-linear functions. It could be anything now. They could be trigonometric, they could be linear, they could be cubic, quadratic, whatever. So we're above and below by the curves, that and that. And on the sides, by the lines x equals a and x equals b. If the region is bounded by curves above and below, and the sides by x minus 2, the volume can be calculated by taking horizontal or vertical slices of the region R. So what that means is to say we have, I'm going to use a rectangle or a square. To find the volume of this object, we could do it with respect to the x-axis, where we take a slice of this function, this region, this is the region R, at one point x, and then it could be from y1 to y2. Then take another one, this is x1. Then we take another one, x2, from the same region, y1, y2, and so on and so forth. And if we add up all those, then we get the volume of our object. So we first find so we have to first find what this area is. Area of the cross section. That's what we found here, this first one. We do that, so it's the area is from y1 to y2 of our function with respect to y, since we're changing with y. Because remember, y1 and y2 is defined as some function g. G of x. So this and this are our functions defined by whatever the equation is, the moving object is. So that's the reason we take a differential with respect to y. Okay. Next, we integrate from x equal a to x equal b to get the volume. Again, this is the beginning, that's a, and that's the end. Because between a and b, we take each of these slices and create our volume. So our volume is the integral from a to b of ax with respect to x, which is from a to b. Remember, a we defined earlier as y1, y2 of our function. Since this one was with respect to dy, and then this part, the outer part, is with respect to x. So let's first find the area, and then we find the increments of each step. So this is if we did it with single x's between the x and y. What if we take it from the other direction? We're going to have the same picture. From here's A, here's B. That's Y1, that's Y2, let's call that C, D. And we have a box in 3-dimensional space. We can take them with respect now with the slices perpendicular to the y-axis and creating these areas. So for another one here, it creates another area box. And we just add up all those and we'll get our volume. All right, so for this one, what we're doing here is integrate from, we have x1 to x2, but x1 is a function with respect to y. Because if we take this one here, it corresponds to that value. And x2 is that value. Because in other words, if we take it with the fixed value is what our functions are integral by. So x is a function of y. So that defines our area. And then y goes from C to D, from C to D. So our integrals, our volume now looks like this. Well, let's do the area first. The area from C to D, this is with respect to y, is found by, we're going from x1, which is h1y, to x2, which is h2y, from C to D. So since we're starting with respect to the x bounds, we take derivative or integral with respect to x. And the y's are from C to D. So yeah, whatever's on the inside is what defines our area. So we're changing with respect to x in this first one. Starts here, it moves. And then the last one is when we look at all the areas together. They will give us the same answer. We get the same solution. Oh. Actually, okay, that's a great question. How do we know when it's dx, dy, dx? Very good question. It does matter because if we had, let's look at this last two we just had. They're going to give us the same answers. So here's dy dx. So since we start off with y, our first integration has to be with respect to our y values. Yes. And y is a function of x. Because now once we finish this, the only variable we should really have left now are x's. And then that's we have only x's left, so then we take the integral from a to b. If we started with x, then we have to rewrite our equation so it's a function of y. So this area now, if we have dx first, then our first integration has to be relative to the function with respect to y. Because now once we do that, the only variable we'll have left, because all the x's will have been replaced with x1, x2. So all we'll have left are the values of y, and that's when we take the integral with respect to y in the last step. That is the tough part that we're going to be looking at in these examples. Excellent question. Yeah, so it doesn't matter because we'll get the same answer, but if whatever we choose, that will define our bounds of integration. And who do we have to thank for this? Yep. Fubini's theorem. This is the stronger form. Because his concept is going to be the same, and we'll get the same answer no matter how we integrate. But since we have our variables that are now going to be defined by functions, we have to define our bounds as well. So f of x is a continuous and differentiable function on a region R. Then two things can occur. The volume defined by this double integral can be written as a integral of AB, the integral of g sub 1 of x, g sub 2 of x of our function. Now, since these are functions of x's, that's what our y's equal. So since we have to first integrate with respect to y, that's what this first part tells us. Once we get that, we'll have values of all our y's are going to be gone with values of x. So then we do our dx, integral with respect to x, on the second bound. Now, this occurs, our region is defined by our x's being bounded by a and b, and our y function is defined by the functions g1 and g2. Since g1 and g2 are functions with respect to x, g1 and g2 must be continuous on the domain, on the closed interval of our x, AB. Because this part defines what we're dealing with, and so our y has to be defined within those bounds. And it has to be continuous because in order to be differentiable, they have to be continuous. And if you could take a derivative, then you could take an integral. So these are the restrictions. R is defined by the boundaries of x, which is a and b, and the boundaries of y, which are the functions g1 and g2, which are continuous in the interval ab. Now, if we switch those, we have the same volume. Our function f of xy dA is now going to be switched, which h1 of y, h2 of y. Since these are functions with respect to y, that's what defines our x1 and x2. So our first bounds of integration has to be with respect to x. Because x is a function of y, all we'll have left are y values. Then we can take the integral with respect to y from c to d. And our region R is defined by the bounds of our y value has to be between c and d, and our x's have to be between h1 of y and h2 of y. Because they're functions of y within that bounds, h1 of x and h2 of x are continuous. On the closed interval. Why the closed interval? Because that's exactly where the inputs remain. All right, let's look at a couple of examples. Yes. Well, for this level of math, yes. When we get to higher level maths, then you can have uh, variables where both integrals, the first integral and second integral, are functions of the same variable. So, I mean, you can have trig functions, you can have polar coordinates, you have all this stuff. Again, those are in higher level maths. So yeah, it's taking double partial. That's exactly what it is, but backwards. You say it's partial integrals. And yet the second one should have finite numbers that once we take the integral, we'll have an equation with respect to that variable. We have to be able to plug in numbers and to get a solid value, because the volume has to be a solid number. Great questions. Find the volume of the prism whose base is the triangle of the xy plane. So let's look at that. We have the xy plane bounded by the x-axis with this one and the line y equals x and x equals 1. So we're looking at this region here of the prism. And our function, the top bound, this is the lower bound, because remember, what our graph looks like here is we go to 1 and the graph there. So this is what our prism is going to look like in the 3-dimension, and it goes up from there. So that's the prism that we're looking at. It's asked to find the volume of it. We know we have two integrals. Our function is 3 minus x minus y. So y is defined as the equation y equals x, and x goes from 0 to 1. So since y is a function, that's the innermost. And since y equals x, and x goes from 0 to 1, y has to go from 0 to whatever x value we have. So that's what y defines. So this one goes from 0 to x. So we're taking with respect to y first. That'll give us the area. And then x goes from 0 to 1. That's the dx value. Now, notice here on the on the y values, even though it says y equals x, when x equals 1, then obviously y equals 1. But it's a general formula. We have to use this as a bound. So however far x goes, that's what y goes. That's why here we have to use the y equals x. And remember, after this first integration, we only want the values, the variable x, to be left, because that's where our last integral is going to be over. So that's why we have our bounds from 0 to x. So first thing, let's look at this one. It becomes the integral of 3 is 3y. We're taking with respect to y. Integral of x is a constant, xy, minus y squared over 2 from 0 to x. All right, so from x, anywhere we see a y, we put an x. X times x minus x squared over 2 minus anywhere we see a y, put a 0, and that's going to be 0. So our equation now becomes we could combine these two if you want. So this would be 2 over 2. So now that takes care of the innermost. The outermost is 0 to 1 of our function 3x minus 3x squared over 2 dx. Because now notice there's no more y's. All we could do is integrate it with respect to x, which is 3x squared over 2. The 3 over 2 is a constant, it stays out in front. So this one becomes x cubed over 3 from 0 to 1. The 3's cancel. So we're integrating 3x over 2 minus x cubed over 2 from 0 to 1. Start with 1. 3 times 1 squared over 2 minus 1 cubed over 2 minus, replace x with 0, we get 0. So we have 1 squared is 1, 1 cubed is 1, so it's 3 over 2 minus 1 over 2 equals 2 over 2, which is 1. All right, let's look at switching our bounds of integration. Okay, so originally we were going from 0 to 1 and from 0 to x. This is what y equals. We went from dy dx. We want to now switch it so that our bounds of integration are from dx to dy. So the outermost, remember the bounds of that one are c to d. So we'll find out what those are in a second. What we have to do, see originally what was the first one? It was from 0 to x, yeah. What we have to look at now is when we switch these two, we know y equals x. Let's look at the picture first, because this is making much. We have to be able to connect it to this. Because remember, when we took this integral with respect to y first and then x, we found the area under the curve this way. Now what we want to do, we have the same graph. Now we want to find it this way. So, and remember, areas under a curve is from the function below there. So here we have x equals 1, and here's the function y equals x. To find this area, remember we're going with respect to the y-axis here, our integrals are going to be from this equation minus the area here. Because the integral of this one will find us this area. So if we take the area under this curve, subtract this, all we're left is with this area. That's what we're trying to find. So in the first one, we have what? With respect to y, our high point is 1, and it goes down to 0. So that's our value y. Remember, we're going to take this high point minus the function y. So that is our area integral. Now, since our function here is y equals x, when x equals 1, y equals 1. So we take the bounds of y are from 0 to 1. So that's the hardest part, because this one here is pretty straightforward. The area, the volume, actually, integrals are areas under a curve. So if we're taking this one with respect to the x-axis, that's just straightforward. But now we're taking it to the y-axis. So we first have to change the bounds. So our bounds are from y to 1. We have 3 minus x minus y dx dy. We'll do the first one with respect to x, which gives us 3x minus x squared over 2 minus yx from y to 1. Because those are the bounds. From 0 to 1. We got 3 times 1 minus 1 squared over 2 minus y times 1. Minus 3 times y squared over 2, y times y. Three minus 1/2 minus y minus 3y plus y squared over 2 plus y squared. Okay, so this is 2 over 2. So this is 6 over 2, so it's 5 over 2 with both of those, minus 4y plus 3y squared over 2. Take the integral of that, we get 5 over 2y minus 4y squared over 2, y cubed over 3 from 0 to 1. So we get 5/2 times 1 minus the 2 goes in there twice. 1 squared is 1 times 1 minus 2. The 3's cancel. So we get plus 1/2 minus, since they all have y's, it's 0. Minus 4/2 plus 1/2. 5 minus 4 is 1, plus 1 is 2/2. It equals 1. So they get the same answer. All right, let's look at another example, because it's going to be, we use the same concept here. Except in this one is the one we saw in Calculus 1, that we had to use the squeeze theorem to find the value of it. So calculate the double integral of this sine x over x dA, where R is the region of the triangle in the xy plane bounded by the x-axis. In the line y equals x and x equals 1. So that's our R. So if we see this, our x values are bounded by 0 to 1, and our y-axis is bounded by 0 to x. That's we just started there. So our integrals of our function sine x over x, since this is a function of x, dy dx. So our bounds are from 0 to x, 0 to 1. The integral with respect to y, there are no y's, so it becomes y times sine x over x from 0 to x dx. Taking the integral, we replace all the y's with x first and 0, so it's x times sine x over x minus 0 times sine x is 0, so that's irrelevant. Simplify, the x's cancel. So we have sine x dx. The integral of sine x, remember, using our unit circle, sine, cosine, negative sine, negative cosine. Derivatives go in this direction. Integrals go in that direction. So integral of sine is negative cosine from 0 to 1. So negative cosine of 1 minus negative cosine of 0. Negative cosine of 1. Cosine of 0 is 1, so it's plus 1. So negative cosine of 1 plus 1. Four, 5, 8, something. Now, let's look if we can reverse this. This is example 2. So what we're looking at is, can we find the volume of sine x over x dx dy? Well, first off, we can't, the bounds are irrelevant here right now, but we'll look at what they'll be in a second. Originally, we had these bounds, 0 to 1, and then 0 to x. Now we switched from dy dx, dx dy. The bounds that we're looking at here. So here we had y equals 0 and y equals x. And then 0 to 1. So our x, this is x equals 0, x equals 1. We know our x equals the y of x, y equals x, but in our graph, remember, x went to 1. So our bound so with this one, our lower bound is x equals y, because we have to, this is our lower function. So x equals y. And this is the one we're going to subtract from it, x equals 1. Remember, whenever you have two curves, let's say we had these two curves. Here's x squared and here's y equals x. The way you find the area between there is take the area of the curve on top, which is y equals x, and subtract it from the curve on the bottom. So it's x minus x squared. That's how you take the area of it. So that's what we have to do here. Take the top one, since we're going this way, take the top one minus the bottom one, which is y. And our y is bounded from 0 to 1. The problem is here. Sine x over x does not have an integral, because that's one of the special functions we had in Cal 1. So this is not possible, because this doesn't exist. Not as a simple antiderivative, I should say. So whenever you change the direction of integration, if you have multiple curves, the farthest right goes on top, and the farthest left goes on the bottom. Here's a note. There is no general rule for predicting Which of the integrating or integration integrations will be a good one or will work? In other words, if you try to do this one dx first and it didn't work, just go back and do the other one. All right.
Could you explain why it doesn't work again?
For here, this is the exact one here. Oh, because this function sine x over x, there is no integral. Because remember, the integral, whatever we find, this has to be the derivative of it. So the integral of sine is negative cosine, but the integral of 1 over x is ln x. But it's not ln x cosine x because we need to have a product rule. There's nothing added, subtracted to it. So these are two functions. This is two functions that are not possibly be hooked together. That's as simplest as I could put it. Is there is no integral for sine x that would give us sine x over x because it's two separate functions when we integrate them. Which is why we had to take the integral of with respect to y first. Because when we got the y and we substituted x in there, it canceled the denominator. Now we're left with only one function, sine x. All right. I mean, it's the only way I can say it is there are some functions that are not possible to integrate, which is why I gave you also those cheat sheets of all the integration rules. Sine x over x. We could find the derivative of it by using the squeeze theorem from Cal 1. We took the derivative of, we know that what's smaller than sine x over x? 0. What's larger than it? We said is cosine. So we integrate those and we got the same value at both ends, or one sine x over x cosine x, or even at just sine x, because sine x is greater than sine x over x. So, and if we look at the values, this one is bounded by 0 or by negative 1 and 1. So they could both be equal to this one here. This one, the sign here has to be 1 because it has to be greater than this one or equal to. So that means sine x over x, since both of the end bounds are the same, that means sine x over x is equal to 1. Because of that, there's no formal proof other than using a squeeze theorem. We can't integrate it. I wish I had a better answer for you, other than it just doesn't exist. Okay, now let's look at using horizontal cross sections. Because up until now, we've been using vertical cross sections of our graphs. Any tips on how to find them better? Yeah, actually, yeah, the next checks the next chapter becomes a lot more difficult because we have triple integrals. Yeah, actually, what you have to do when you're going to switch the bounds of integration. Let's say this is dy dx. Whenever you switch the inner bounds of integration, and this is 0 to 1, we know that since this is the inner one, that has to be a function of y. It is y, and it's a function of x, presuming that last. The easiest way to do that is take both of those equations and solve for x. Because if we're going to reverse these, we have to have a function with respect to x. So solve for x for this one, we get x equals square root of 2. And for this one, x equals y over 2. And then looking at whatever graph you had, whatever graph is further to the right, that one goes on top. Either it's 1 or 2. So let's say on our graph we had y over 2. Well, so that's how, oh, that's not x. This is an x function. It'll look something like this. And y over 2 is a very, very slow rising one. And we're looking with respect, doing horizontal cross sections. So whatever we have, let's say this one's on the bottom. Because whenever you do the integration and do the top minus the bottom, it has to be a positive answer because the volume is a positive amount. Okay, let's look at this one then. Here we have, I'll give you the graph. This is the region we're looking at. This equation is one minus x. This equation is x squared plus y squared equals 1. It's part of a circle. I want to know what this area is. If I did vertical, or if I'm going to do dy dx, then the bounds of my integration are just that. Is the outer one goes on top, so I solve for y. So it's 1 minus x squared. And the lower one is 1 minus x. And then the x goes from 0 to 1. Let's say I wanted to switch those. Now I'm going to go this way. So my outer function is this one. So I have to solve this one to solve for x. So x is equal to square root of 1 minus y squared. And this one is, since I solve for x, I get x equals 1 minus y. and then from 0 to 1 on the y-axis. So if you're going to switch the order of integration, you have to look at your equations. The outermost, because you're going this direction now, so the higher one goes on top, the lower one goes on the bottom. You have to take these equations, the formulas for them, and solve for the variable. Since this has to be an equation with respect of x, this has to be an x. Let's do this example here, and it'll show this much easier, much better for us. We're gonna do it both ways. Yes, because we're looking at, whenever we do integration, it's always perpendicular to the axis. So if we're doing it with respect to the x-axis, it's got to be perpendicular to it. If we're doing it with respect to the y-axis, it's got to be perpendicular to it. And the reason also it's right to left is because, let's say we had two functions. Let's say they crossed here. Anyway, let's go from A to B. If we're going, this is y equals x1. This is y equals x2, or y1 equals. So if we're doing it with this like this, then we have to take the higher function, which is x1, and subtract the lower, which is x2, because all we want is the region between there. The upper one finds the area underneath it. The second one finds the area underneath that. So if we subtract the two, what we're left with is that space, which is why we would write our function like this. Now, if we're going left to right, then this would be our upper function, but we'd solve for y2. So now it'd be y2. Let's say the y-axis was here. So it'd be y2 minus y1. So if we're doing it vertically, whatever's on top goes on top. Whatever's on the bottom goes on the bottom. If we're doing it horizontally, whatever's furthest to the right goes on top. Whatever's furthest to the left goes on the bottom. And we have to algebraically solve those functions for those. So let's look at this last example here, and then we'll talk about the properties. Sketch the region of integration of the integral. Since we're doing with y first, with this one, and this is our function, our bounds of integration have to be functions of x. So we have y1 equals 2x, y2 equals x squared. And since our x's go from 0 to 2, that's our bounds really, our graph will really go from 0 to 4 on the y-axis, because if x is 0, those are 0. If x is 2, we get 4. So we know that's our range. And our x has to go from 0 to 2. So the first one is 2x. 1x is 1. 1x is 1, y is 1. So that's the graph. That's equals 2x. Then the other one is x squared. What we're looking for is this region right here. And this is our function. 4x plus 2 dy dx. So our y values are, the upper one is 2x and the lower one is x squared. That means the outer one is from 0 to 2. What this is looking for is, we're going to look at the second one minus the first in a minute. But now we're doing this integration because this one is higher than this one. So if we integrate these two, we get 4x squared over 2 plus 2x from x squared to 2x. So anywhere, this simplifies. Anywhere you see an x, put a 2x squared plus 2 times 2x minus x squared. X squared squared plus 2 times x squared. And simplify, so we have 2 times 4x squared.
I think you forgot a 2 when you
Where?
were putting in the x squared
On this one?
on the first one.
Oh no, I cancel those out.
No, because the minus and then x squared squared,
Oh,
there should
here.
still be 2.
Yeah, there. Right there, yes. You have great eyes, thank you. So over here, if we have 4x, this changes those signs, so it's minus 4x to the 4th minus 2x squared dx. 8x squared minus 2x squared plus 4x minus 4x to the 4th. Six x squared plus 4x
I think it should be 2x to the 4th because the 2 wasn't. I don't think the 2 is supposed to go inside the parentheses. Yeah, because like how in the first one, you did 2 and then it's x squared and then you only replace the x. So the 2 is on the outside. But then right here on the other one where you forgot the 2, you put the 2 on the inside.
Oh, here you mean?
Yeah. So shouldn't the 2 be on the outside, not the inside?
It's a coefficient. Yes.
So it should have been 2x to the 4th, not 4x to the 4th.
Here.
Mm-hmm.
Right. It's 2x squared, 2x. So it's 2x sounds 2 times, that should be x, 2x there, minus 2x squared It's 2x squared plus 2x from x squared to 2x. So the first one with respect to that. So it's 2x squared plus 2 times 2x minus 2 times x squared squared plus 2 times x squared. Two times 4x squared 2x to the fourth 2x squared. 8x squared plus 4x minus 2x to the fourth minus 2x squared. Eight minus 2, so it's negative x to the fourth plus 6x squared yes. Actually, you're perfectly correct there, yes. Now integrate with respect to x. We get x to the fifth over 5, x to the third over 3, x squared over 2. That becomes a 2. That becomes a 2. And since they all have x's, this one goes to 0, so we have negative 2 over 5, 2 to the fifth, plus 2, 2 to the third, squared, minus 0. 32, 8, 4. Sixty-four minus over 5 plus 120 over 5. One 56. No, 56. No. Okay, that's should use a calculator. 56. Okay, well, I did something wrong. But I want to do now is I want to change these bounds of integration and see if I get the same answer. If I get the same different answer, then I did something wrong with one of the two. I'll check it again. So let's see this. We had 0 to 2, x squared to 2x. So let's switch the bounds from dx dy. So these are y equals both of those. So this one becomes x equals square root of y. This one equals x equals y over 2. All right, so which one's now on a bigger side? Square root of y like that, y over 2. Y over 2 square root of y. Because it would look like this. And the bounds again now, since our x's were from 0 to 2, from 0, if I put 0 in there, it's 0. If I put 0 in there, it's 4. So let's integrate this one now. Dx dy. So the first one is 4x squared over 2, 2x. So that becomes, those simplify as 2. So we have radical y squared plus 2 times radical y minus 2 times y over 2 squared, 2 times y over 2. Radical y squared is just y. Two y squared over 4. 2's cancel. Two y plus 2 radical y. Those cancel. Just 2 minus y. 2y minus y is y. Now we got to integrate that part. Y squared over 2. Yeah. We have to add 1 to it, so it's 3 over 2. 3 over 2. y cubed over 3. Four squared over 2, 4 over 3 times 4, square root of 4, 4 cubed over 6 minus 0. 16 over 2, 16 over 3 times 2, 64 over 6. So multiply this one by 3, by 2, they're all 6 on the bottom. It's 48 divided by 6 is 8. So yeah, when you change the bounds of integration, you have to set those equal. This is the y first. This equals y equals x squared, y equals 2x. Solve for the other variable. I solve for x, I get that and that. And then the bigger, when you look, if you graph the two pictures, x equals y squared is that parabola type. Y over 2 is that linear. So since this one's further to the right, it goes on top. So that one goes on top. Basically, you should always, it's always going to be switch the two. Since this is top, 2x is on top of that, it'll switch right here because you switched x and y. And then to figure out the y values, these are my x's as my inputs. What does my y equal? 2 times 2 is 4. So 0 to 4. Let me see. Let me do the first one again because we should get the same answer. I did a brain fart somewhere. So we had 0 to 2, x squared to 2x, 4x plus 2 dy dx. So with this first one, we take it with respect to y. So we have 4xy plus 2y from x squared to 2x dx. Now anywhere I see a y, I put 2x. Minus anywhere I see a y, I put x squared. So we have 8x squared plus 4x minus 4x cubed plus 2x squared. It's 8x squared plus 4x minus 4x cubed minus 2x squared. So we have minus 4x cubed, 8x squared minus 2x is positive 6x squared, plus 4x. Now integrate it with respect to x. X to the fourth over 4, x to the third over 3, x squared over 2, from 0 to 2. The fourths cancel. That becomes a 2. So I have minus x to the fourth, 2x cubed, plus 2x squared. Negative 2 to the fourth, 2 to the third, 2 squared, minus 0. Minus 16. 8 times 2 is 16. 4 times 2 is 8. So 8 has to be the answer. I don't know where I went wrong the first time. I squared it instead of the. That's where I messed it up. I squared this one, and it should not have been squared. All right, so the answer is 8. That's our. So as I said, if it doesn't work, try it again, and always use guesstimation to see if it's correct or not. And lastly, let's look at the properties of double integrals. They're the same as single integrals. If you have a constant multiple, that constant can go out in front. The sum and difference, if I have the sum and difference of two functions inside the integral, I can split them up. Domination. This one's interesting because it's whatever is larger. If we had our double integral, and that's positive, only if and only if the function itself is positive on R. Conversely, if it's negative, if only if that's negative. If one function is larger than another one, if and only if the individual functions themselves are the same order. And the additive property. This one is we're going to be use this more than the other ones. If you have a function that's discontinuous or on both sides of an axis, or as if you had a function just like I had earlier, we could take the integrals for this is the region R. The first region could be from A to 0. That's our first region. And the other integral could be from 0 to A. That's our second region. So R is simply if you add them two together. All right, so you can combine multiples. So are there any more questions about converting the domains, the bounds of integration? Or did I answer? Hopefully I didn't confuse you more than you were before you asked the question. It's just that whenever you take them, remember the inner bound. The inner bound is a function. Let's say if it's y equals, let's say x squared, 1 over x. Since this is an equation with respect to x, that you integrate it with respect to y. Because after you finish this, our function is going to have only the x's in there. So the second one has to be with there. Let's say that equals 1, that equals 0. Now this, when we switch them, solve for the other variable. So in this one, x equals y squared, x equals 1 over y. And then you look at which one's larger, which one's smaller. So because this is what x equals, and that's what we're taking the first one with respect to. Now, to figure out the y bounds, look at our bounds. So it goes from this is indecisive, so it's from 0 all the way to 1. So you have to plug in those original values for x inside there and see what the bounds are. Other than that, very good question. The z is the third integral. Is because when you ever have z equals a function of x, y, you're going to have that type of integral. Yeah, and sometimes you'll see if it has it in there. If it has it in there, that means your equation has to have the z in it. If you just have the equation like this, then that is your third dimension. That's what f of x equals. So that's what you'll have there. And that's what we'll do in the next section, in the next chapter. We're going to deal with triple integrals from here on out. But what this section did is now we could transform our bounds of integration from dx dy to dy dx and be able to convert the bounds appropriately. All we have to do for the third dimension is just add one more step to it. And that's the third dimension is the k-axis, and that has to be an integral. I mean, not integral, but an integer. All right. Because the next chapter, we're going to talk about what are called shadows. And let's say we integrate like this. Whatever these last two bounds of integration are, that's where here's our object in three-dimensional space. Our shadow will be on that plane. So we'll have, so this shadow is going to have bounds x1, x2, y1, y2. And this is our three-dimensional domain. So that's what we're looking at next. But the basic rule there is whatever the last two terms of integration are, that's where the shadow is going to be, and we take it from there. All right, everybody. I will have those videos and the solution sent out to you ASAP. So for this and the next section. So you could look at those and we can move on. You remember, whatever, as soon as 6 o'clock comes on Saturday, whatever I haven't gotten to you, any videos, solutions, or lectures, is not going to be covered. Because I want you guys to be able to have time to go over the stuff, assimilate it, apply it, and take the tests multiple times so you get the best grade. 6 p.m. Saturday, yeah. So whatever's not sent to you on remind after 6 o'clock is cut off the course listing. We're not going to cover it this semester. I'll send you a video over it, but it won't be covered on the test or anything. It will be an FYI. All right, you're more than welcome. Have a great day. Be safe, and I'll see y'all. Actually, I'll be on tomorrow also, because tomorrow we don't have class on the 4th, and I want to try to cover as much stuff. So I'll finish chapter 15 tomorrow. If I don't get the video done and send it to you, so we just talk about it tomorrow. All right. Have a great day, everybody. I'll talk to you tomorrow.